Hey everybody, so I wanted to make our video for our Chapter 6 notes. Sorry for being a little delayed with these. Things have been a little more hectic than usual. So I know a lot of you guys have been struggling a little more with these concepts, probably because we're introducing so much at once, and I'm hoping that this video will help clarify some of these things, or at the very least help you pin down where your issues are arising so that I can try and be more helpful. So, basically the goal of this chapter is that we have defined groups and given some definitions of what they may be. And so the purpose is to introduce several relatively simple examples of groups so that we have a little more to work with in terms of visualization and actually studying these objects. So we're going to introduce 5 different groups: cyclic groups, abelian groups, dihedral groups, symmetric groups, and alternating groups. And we're going to also introduce some visualization techniques. And we're also going to study various things such as permutations, which are really one of the most important things about groups. Or basically the permutation group is one of the most important examples of groups. And the reason for this is historically, permutations were the things originally studied by algebraists and really what motivated the mathematical definition of the group that you saw in the previous chapter. So permutations, while they are not the only things that we can study, they're quite important, and this is actually realized through Cayley's theorem that we'll talk about towards the end. So first are cyclic groups, and a group is cyclic if it can be generated by a single element. So finite groups typically describe symmetries of objects that, finite cyclic groups describe the symmetry of objects that only have rotational symmetries. So these kind of objects are examples of this. So what you should notice is if I try and do any kind of flipping, it won't take up the same space, but I am able to do certain amounts of rotations and it will preserve the same space. And so with this, the key thing here is that it's generated by a single element. So remember, a generator is an element of the group or an action that when performed over and over and over again, it can generate let me rephrase this. The generators of the group are the building blocks, meaning that all other elements or actions can be built from those objects. So if we have a single generator, then what this means is every element in the group is built from this one single element. So for these pictures here, what we can see is depending on the number of arms, so to speak, then there are a certain number of rotations that we can perform, right? Here we can perform rotations of 2 pi over 3, here we can perform rotations of 2 pi over 4, and here we can perform, I'm not going to count them, but something like 2 pi over 10 in terms of rotations. And the idea is we can take one single rotation. So for instance here, taking this point and rotating it to here, which in turn rotates everything else, that one single rotation performed over and over and over again can realize all 4 possible orientations of this object. So now what I want to mention though is just because I'm saying that this is a generator, right, using the kind of article a, meaning that it's not the only one, there could be many other choices. We're simply trying to provide what I would call a canonical choice. So cyclic groups are things that rotate, and that's really the only thing that they can do in a group-like manner. So the order of a group is the number of distinct elements in that group, and we typically denote it with these kind of absolute value bars. All right. So the cyclic group of order n, which means it has n rotations. So for instance, this would be C3 because there's 3 rotations, and C4 because there's 4 rotations, is denoted by C sub n. All right. And so here we have exactly what we just said: C3, C4, and C10. Now alternatively, we often call Cn Z sub n. All right. And this is due to the fact that these rotations behave exactly the same way as modular addition did way back in chapter 1 last semester. So basically the idea is what you can think of as Z sub n is if you write down, for instance, let's pretend like it's Z sub 5. you write down the numbers 0, 1, 2, 3, 4, 5, you wrap them in a circle and glue 0 to 5, then basically addition just spins you around this little band that you've just created. All right? And so when I'm saying 5 here, typically we don't include 5, but I'm wanting to allow us to glue in an overlapping way. If you don't want to do that, you can think of just writing down 0 to 4 and gluing 0 and 4 together side by side, not on top of one another. But regardless, we have this kind of rotational feature, which is why I typically called it clock arithmetic when we were referring to the integers modulo n. So these are the basic cyclic groups, and let's say cyclic groups are pretty simple, so there's not a lot of wiggle room in terms of how they can look or what they can be. All right. So a common way for us to denote the elements of a cyclic group is just with the integers 0, 1, 2, ... n minus 1. So this would be a representation of the elements in C sub n. 0 is always thought of as the identity in this group, and 1 is thought of as the single counterclockwise rotation, or you can think of it this way: 1 is always denoting the generator or the canonical generator in the cyclic group. So if we take this set and realize them as integers, right here they're labels. So what I mean by this is these are labels, they're names. They have no real arithmetic meaning right here. These are simply labels. I could have just as easily have said Josh 0, Josh 1, Josh 2, ... and said those are the elements of my cyclic group. But now the next line is saying that when I pretend like these are actually integers, so when I realize them inside of the arithmetic land that we've always lived, then this set is closed under addition modulo n. All right? Now this was something that we discussed back in chapter 1, that when we think about the integers modulo n, we have a notion of closure because we have this so-called wrapping around feature that I tend to say. The idea is once I get to n, right, when I add 1 to this and I get n, I get mapped back to 0 and I just keep cycling through. So the Cayley diagrams of cyclic groups are pretty easy to draw and also are very informative, right? The idea is if I have C3, then the idea is I start at 0, which is the identity, I add 1, which is now the generator, and I add it again and I get a new element, but when I add it again, I'm back here. Similarly for C4, all right? So in this setting, the set Z sub n, which once again can be thought of as C sub n, right? Z versus C, and the binary operation, which is just addition modulo n, form a group. So remember, in our old definition, we need that we have what? A set, a binary operation, and we need there to be certain properties such as associativity, which addition has. We need to have a notion of an identity, which is 0, and then we need a notion of inverses. Now, we don't have negative numbers, but the idea is if you choose a number from this set, let's call it A, then its inverse is just n minus a, whatever it takes to get to the number n so that it's mapped back to 0. All right? So these are some very simple cyclic groups. You can probably come up with many, many others, but ultimately they all end up being, in an algebraic sense, equivalent to these, or they're basically the bigger ones as well. But the idea is what I mean in equivalent in an algebraic sense is their Cayley diagrams, when I remove the labels, will all look the same for cyclic groups. So there's not a whole lot of wiggle room here, even though we can call them different things. So just to illustrate this fact, I can also think of cyclic groups in terms of multiplication, right? So here I had addition with integers. So I can also think of them in terms of multiplication. So the idea is if we think of R as being a generator of a cyclic group, then we can denote all the elements of R with this kind of power notation, right? So the idea is now I'm going to use 1 as the identity because 1 is the multiplicative identity. And then instead of adding things, I'm thinking of multiplying them, all right? So what you should think of is this is just a different notation, all right? And so really the way that you can think of this is, right, we have these circular objects, so let's let R be the complex number e to the 2 pi I divided by n. Now, if you haven't had much experience with complex numbers, then what this really does is it traces out the unit circle where we traded out x's and y's for real and imaginary parts. So this guy represents the unit circle, or points on the unit circle. The number n tells us how many stops we make along the way when we do our circle. So when n is 3, we make 1, 2, 3 stops, right? And then when n is 4, we have 4 stops that we make. So the idea then is we have the same exact representation, the same exact Cayley diagrams, but now I'm thinking about multiplication of complex numbers versus thinking of addition of integer numbers. All right. So in this setting, the cyclic group is the set of complex numbers with the binary operation of complex multiplication, and the identity is 1. Now, before you fret and think that we have just different complete ways of thinking about these things, actually later in the course we're going to prove that addition on real numbers and multiplication on real, or let's say on non-zero real numbers, can be shown to be equivalent in some sense. So this isn't some far-fetched thing. The idea is actually that these objects are very similar for a very real algebraic reason called an isomorphism, and this is something we will introduce in later chapters. So what are you to be taking from this? You're to be taking that we have two distinct representations of cyclic groups, additive and multiplicative. And the idea is they both end up giving us the same Cayley diagrams, but they give us two different ways of understanding what a cyclic group can be. And the idea is sometimes one view is more helpful than the other, but now we have some very concrete ways of viewing cyclic groups, other than just these pictures that I randomly decide to draw. All right. So now that we have this, basically, as this is saying, like I just said, the choice of using addition or multiplication doesn't change the actual group. It only changes our notion of, or of how we decide to do notation. Now, there is actually a unique infinite cyclic group. And now what I mean by unique, if I want to use an additive notation, then there is a unique cyclic group, and it is the integers with addition. And let's say here, I'm really meaning countably infinite. All right, so meaning that I can kind of enumerate all of the possibilities. And basically what I mean here is the set of the integers with addition is a cyclic group. And using a multiplicative notation, we use the following. We just raise it to a bunch of powers. Now, this goes back to last semester when I was telling you guys that we can think of the integers as somehow wrapping around. So before we had this problem way back in chapter 2 or 3, where I asked you to determine how many actions were needed to generate the infinite integer group. And most of you said you need 1 and -1, and I didn't really take any points, but what I kept saying was you only need one generator. And the reason is kind of as follows. If you think of the integers, so think of a circle. All right, so let's go back let's say, right, we can pretend like this is a circle. And what I've done is I've chosen 4 points on the circle, and I got z sub 4. If I chose 5 points, I would get z sub 5, but I don't get the whole circle. So what you can imagine, this is really more of a thought experiment, is if I were to choose an infinite number of equally spaced points on the circle, then I actually would still have some gaps, in a sense. Because the idea is this circle has, right, I may be using words that we haven't ever used before, but uncountably infinite spaces. So what do I mean by uncountably infinite? Think of the real numbers. For every integer, there's a bunch of things in between, so there's a lot of stuff. The integers leaves gaps. So even though I couldn't visualize it, by placing the integers on this circle, there would be some gaps. And that could be thought of as something like z sub infinity, or just z. It's the circular group where I kind of think, okay, here's 0, and it wraps around ever so slowly to infinity, and then all of a sudden infinity jumps over to negative infinity and keeps wrapping around and around and around. Now, this seems like a very strange way to visualize things, but what you can think of is if you want to do things modulo infinity, then you would glue the infinities together. And this is why we can think of the integers themselves as a cyclic group. So this is just to give you an example of an infinite cyclic group. The other ones, if they're, let's say the other ones that have more exotic types of representations are notoriously difficult to write down. So this is your really only working definition of an infinite cyclic group that you would ever use. Similarly, one thing that we proved last semester was the following. If any number in this set is relatively prime to the number n, then that number will generate z sub n. So what we have is basically, as I'm trying to generate the integers modulo n, I start to get repetition when they have numbers in common, right? So what do I mean? If I have z sub 8 and I choose the number 2, then I'm going to get 2, 4, 6, 0, 2, 4, 6, 0, 2, 4, 6, 0. And I'm never able to hit the odd numbers because there is a 2 in common with the 2 and the actual n right here. So this is simply a proposition that we could prove that lets us know that for these cyclic groups, we don't have to just choose the number 1, We simply need to find an object that is relatively prime to the size or the order of the group. All right. So just as I was saying, we can generate Z6 with 1 and 5 because these are relatively prime to 6. We can never use 0 because it's the identity. And we can't use 2, 3, and 4 because 2 and 4 have a 2 in common with 6, and 3 has a 3 in common. However, with Z sub 5, since 5 is prime, all non-zero numbers will be generators. Right? So, and the idea is this angled bracket here in this situation means that this group is generated by this element. Right? So what this means is if I take 1 and add it to itself, it gets 2. And then I add it again and I get 3. And I add it again and I get 4. And I add it again and I get 5. And I add it again and I get 6, which goes to 0. And I add it again and I get 1, which is back where I started. So I've generated the entire group because that's everything in Z6. All right. Now also modular addition, which of course means cyclic groups as well, they look very nice whenever you put them in multiplication tables. All right, and so the idea is what you can see is we start to have this shifting pattern, right? I have this 0, 1, 2, 3, 4, and then it shifts over. So what do I mean? Think of like a Mario game. It runs off the right screen and it comes in off the left. So as I it goes out the left and it comes out the right, or back on the right. Sorry, I was going backwards. So when I go down, the 1 goes over, the 2 goes over, the 3 goes over, the 4 goes over, and 0 came out the back. The 2 goes over, the 3 goes over, the 4 goes over, the 0 goes over, and the 1 comes out the back. So if you create one row of a cyclic group, you, for free, have every other row through this very nice symmetric pattern that happens as we go down, look down the list. Of course, it goes across as well. We just have to rotate in the opposite way, going up, 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 up. All right. And so, of course, there's a million other, or I shouldn't say a million, that seems like a lot, but there are many other things that we could comment on. But one of the most important properties was this natural shift that we just talked about. And so what I've done is I've tried to formulate this observation to tell us how the shifting happens. So the idea is if the labels of the headings use either the additive notation or the multiplicative notation, then each following row is just shifting everything to the left. All right. Now, I'm asking, do you see why this happens? Well, the reason why is really, let's say, because of the fact that every time I add 1, it moves everything over, and the guy at the end pops back at the beginning. There's this very circular feature to the integers modulo n. All right. And so, of course, you can ask yourself what other nice properties you can see, and I'll leave this to you to kind of study and figure out. So, now that we have cyclic groups, or let's say we want to now talk about orbits. All right. And the reason for this is because cyclic groups are pretty simple, but cyclic groups do in fact fit inside other larger and more complicated groups. All right. So before you kind of start focusing in on the picture, just remember what I'm saying here. If you have an arbitrary group, the idea of a cyclic group is you took an element and you generated an entire group using that one element. So what we're about to do is to pick one element from a group and try and see if the group is cyclic. All right, does that make sense? We're picking an element and we're seeing if it generates the whole group. If it doesn't, it will generate something. And whatever it generates is called the orbit of that element, and that's what we'll see. All right. So we're going to consider the Cayley diagram for D3. All right. So remember, this was the diagram for the equilateral triangle. So we had rotations, and then we had flips followed by rotations. All right. Now, this is not cyclic because I have 2 different colors, hence I have 2 different generators. So I'm definitely not cyclic. But look what happens if I choose the element R. Well, then if I apply R again, I get R squared, and if I apply R again, I get E, and if I apply it again, I get R. I have this very circular feature that lives inside of the graph. And so what this means, this is really what we're going to call the orbit, right? This itself is a cyclic group in its own right. Similarly, the outer edge is a cyclic group in its own right. So what we're going to be talking about is the generators of these kind of cyclic groups that live inside of other groups. All right, so within this Cayley diagram, we see that there are copies of C3, right? The 3 circle elements. So, and then the idea is this cyclic thing is called the orbit of the element R. All right, and this is very important. All right, so with each orbit, we need to designate what is generating this orbit. All right, So what I mean is we're going to choose some starting point, okay? And then we're going to apply values over and over and over again and just see how they circle, all right? So for instance, if we go through and we start at E and we apply R, then what we see is we're just circling through and it is generated entirely by R. Similarly, this could be generated by R squared, because R squared is nothing other than two red lines followed by one another, right? To get from E to R squared, it's R, R, all right? So then what do? If I do R squared again, I go R, R, and if I do it again, I get to E, and if I do it again, so I'm just going through the circle, so R squared is also a generator of this. Now the reason is, this is C3, right? The integer is modulo 3, and 2 is relatively prime to 3, hence it can generate the entire group, or the entire orbit, all right? Now, the blue arrows also form an orbit. So what do I mean? If we do the blue arrow, we get to F, we apply F again, and we get back to E. There's this very simple orbit that is very trivial to look at, but it is still an orbit, right? And the idea is the size of the orbit is the same thing as the size or the order of the actual group that it generates. So this orbit is of order 3, and this is of order 2, all right? And so I'm trying to use color to designate which ones goes to which, and typically when we try and describe our orbit, we simply put in braces the actual elements that live inside of it, all right? And every element in a group traces out an orbit, all right? Some of these may not be obvious, but they are there nonetheless, and you might say, well, what do you mean? What about E? E doesn't do anything. You're right. It forms an orbit of size 1, which is just the trivial orbit, okay? And then you might say, what about these other weird-looking ones like F followed by R, which is equivalent to R squared F? Well, the idea is it does generate something. What do? You do blue and then red, and then blue and then red, and then blue and then red. We're stuck in this same little circle, so we have, once again, another orbit, all right? And you have to ask yourself, how many elements are in it? It looks like there's 4, but we've got to be careful. Remember, we're not counting F. We're going blue-red to get R squared F, and then we're going blue-red to get here. So there are exactly 2 elements in this orbit, all right? And you can go through and start figuring out all the other orbits in this set, and here are what you come up with. We see that there are, of course, 6 elements, and we can construct 6 different orbits, and we ask ourselves, how many distinct orbits are there? Well, there's only 5, because these 2 guys have the same exact orbit, right? They trace out this inner circle. Otherwise, everything else has a unique orbit, and they're all of size 2 once I get outside that circle. All right, so now there's a couple things I want to mention here. Now, I've spoken about actually finding the orbit, but I think many of you are still struggling with, let's say, computing multiplications from these kinds of tables. Okay, so the idea is, if you want to figure out how to represent a certain action, it works as follows. So look at the action RF. What I need to do is start at E and get here, and let's say you can choose any path that gets there, but you should try and find the shortest. So, for instance, the action of RF can be represented by starting at E and going red and then blue. So this guy is red-blue, whereas R squared F was blue-red, right? And so if I wanted to compute, for instance, RF times R squared F, I would do the following. I would say RF is red-blue, R squared F is blue-red. So RF times R squared F is red-blue followed by blue-red, which sends me to R squared. So if you want to perform multiplications, you simply need to determine from the Cayley diagram what sequence of arrows represents this node, and then multiplication by that node is performing that sequence of arrows. All right? Now, it's very important to know that in many groups, the order of these arrows matters. And as you can see, red-blue or blue-red gives me 2 different objects, so I have to be very careful to make sure that I'm performing these things in a very precise order. All right? Similarly, I could ask myself, what is R squared F times RF? Well, I would do R squared F times, well, what do we need here? A red-blue, so I would do red-blue, and I get R, okay? So I'm trying to remind you guys of some things that we've learned before and that you guys have been asking questions about. This is how we perform these multiplications, all right? So the order of an element is simply the order of the orbit. All right, so what do I mean? If you want to know the order of an element, if I ask you what is the order of r squared, then you find the orbit of r squared, meaning you do what? You perform r squared over and over and over again until you get to the identity, and then, or until you repeat, however you want to think of it, and then you count the number of elements that are in that orbit, right? All the things that were generated, and that gives you the order of the element. So the order of an element is the order of the orbit generated by G. All right, and so the orbit of E is always E, and so of course the order, so the orbit of E is E, and the order of E is 1. All right, and so if you want to find the orbit, it's just raising all these guys to a power, and this set here is not necessarily infinite, right? Even though I can raise it to all the powers in the world, what we see is there starts to be repetition, right? I have to the power 1, power 2, power 3, power 4, power 5, power 6, power 7, power 8, power 9. But the idea is, even though I'm doing this a bunch of times, I get one single orbit that consists of 3 elements. All right? So this is simply saying you keep raising powers until you start to repeat. All right? So, and the idea is basically the orbit is just all the things you get from applying G and its inverse as many times as you need to do it. So it's really all the things that you can build from the single Lego piece G, right? And so for any group, the orbit generated by G is a cyclic group that sits inside of G. And this is going to be something that we later call a subgroup, okay? So we don't know what subgroups are yet, but basically they are groups that live inside of a group that are still groups in their own rights, right? Now, we also introduced the notion of a cycle graph, okay? Now, the reason that we draw cycle graphs is really as follows. We want to draw all of the orbits inside of a group, all right? So now there's a couple things to know. Every element from the original group will be present in a cycle graph, all right? And we had 5 distinct cycles from before. So what are we going to do? We're going to draw these 5 distinct cycles. Okay. Now, let's say the E, I'm not going to draw, right? There is no real cycle, it's just a node. All right. These 2 cycles are exactly the same, and they're represented by this loop down at the bottom. The other 3 cycles are simply represented by these kind of flower petals that come up off the top. All right. So the point of the cycle graph is to represent a group in a different way. It's to basically decompose the group into all of its orbits. All right. So the way that you draw it is really you need to find all the orbits. You'll put the identity in the center, and then you circle off to represent each of the orbits. Okay. So each cycle or little, let's say, flower petal represents an orbit. And the idea then is if there are cycles within a cycle. Now, what do I mean by such a thing? Think about, once again, the set of integers modulo 8. The entire integers modulo 8 is 0, 1, 2, 3, 4, 5, 6, 7, 8. However, there is another cycle that lives inside of it which is generated by 2, and that is 0, 2, 4, 6, 8, which of course both the 8s go back to 0. So in that situation, if I were drawing that single loop, I would not be able to distinguish the cycle generated by 2 from the cycle generated by 1 because they live inside of one another. We're not able to somehow distinguish between them. And we also don't put colors because the definition of an orbit is that it has one generator. So there's no need to add colors because it's already generated by one object, so there's no need to designate it. The actual cycle that you're looking at tells you all you need to know about the generators of that thing. All right? If you have intersections of cycles, which I don't have drawn here, but you may see in your homework, then if there's intersections, it's actually the case that they have points in common. So nowhere am I saying that these cycles don't somehow overlap, all right? And you might say, what do you mean? Well, for instance, think about the fact that if you're trying to do integers modulo n, the number 2 and the number 3 will have things in common because, for instance, they both divide 6, right? So the idea is they would both intersect through 6, but that's perfectly okay, all right? And of course, cyclic groups are simply just a single cycle, right? So if you're going to draw the cyclic graph of a cycle graph for a cyclic group, it is just the original graph of the cyclic group. All right. So cyclic groups were a big building block to allow us to introduce a few things. Now, abelian groups are another layer of groups that we can have that have a special kind of niceness to them. Now, we've seen them already a few times. So a group is abelian if and only if the order in which I do my operations will not change the outcome. All right. And so the idea of what you should be thinking here is the addition of integers, the multiplication of integers. But things that don't fit here are things like the multiplication of matrices. All right. And so when I took algebra, I don't know how long ago it was, but it was a while back. This was something that my professor liked to refer to as the shoes-socks principle. Right. The idea is there's a distinct difference in the outcome whether you put on your shoes first and then your socks, or your socks first and then your shoes. So sometimes the order matters. But an abelian group is a group in which the order that you perform the operations does not matter. And this is called a commutative group because the underlying binary operation is commutative. All right. Now, just to let you know, in order to check if a group is abelian, it suffices to only check that the generators commute. Why? Well, if the generators commute, then all other objects are built from the generators. And of course, if the building blocks commute, then since I can build everything from building blocks, then everything will commute. So this is something to think about for yourself. All right. And so the idea is if you want to start looking at Cayley diagrams to see, to understand whether or not something is abelian, these are kind of the two basic objects. So if my starting point is here, so this is just some object. The red line is the operation A, the blue line is the operation B. So this is the outcome of A times B, and this is the outcome of B times A. Since these are not the same node, it's not abelian, right? So the fact that I don't have this diamond shape, or something that is a deformation of a diamond, tells me that this is not commutative, or that it's not abelian. However, here, since I end up at the same spot, no matter which way I go, this tells me that this is, at least for these two operations, commutative, right? The idea is there could be other operations for which it breaks, but since this works, this means that A and B, these particular A and B's, do commute. So this object can never occur in the Cayley diagram of an abelian group. In an abelian group, all of these are going to be the things that build your Cayley diagram. All right. So cyclic groups are abelian. Well, why? Well, for one, because the left configuration never occurs because there's only one generator, so there's only one color. And two, basically the more mathematical reason is every element inside of a cyclic group can be written as r to some power. So then that means if I have two different elements, it's r to one power and r to a different power. Well, since r is the same thing in both places, it commutes with itself. All right, so the idea is any action commutes with itself. All right, why? Well, because it's kind of like, do you want to go left first and then left, or do you want to go left first and then left? And if you're thinking that my description of this sounds asinine because there's no difference, that's because it's basically saying that since they're the same exact thing, the same exact action, the order in which I do anything doesn't matter because they're all the same exact action. All right. Now, an abelian group does not need to be cyclic. All right. So you can ask yourself, are there any abelian groups that are not cyclic? All right. And of course, the answer is yes. And you need to try and think about what such an example might be. All right. Now, to kind of think about things further, you can ask yourself, or we can look at the following situations and try and determine whether each of these are abelian groups. All right. So what you need to do is pretty much go through here and you can say, okay, well, I have lots of these kind of diamond or rectangular type shapes, so maybe they are. So then we have to start asking ourselves, is it abelian? So starting here, if I do blue and then red, or red and then blue, I end up in the same place. Starting here, if I do blue and then red, or red and then blue, I end up in the same place. If I start here and I do blue and then red, or red and then blue, I end up in the same place. And then starting here, if I do blue, starting here, if I do blue and then red, or red and then blue, I end up in the same place. And then similarly here, since this little inner circle is of course just, let's say, red over and over and over again, everything works out. So this is an abelian group. And the notation should kind of give it away. It looks like I'm saying there's a cyclic group and another cyclic group being glued together in some way. And we haven't learned what this means yet, but we will later. But loosely what you can think of is this is a Cartesian product like you do when you construct R2. So since each of these are cyclic, it seems like it might be reasonable, or since each of these are cyclic and thus abelian, it seems reasonable that the outcome could be abelian. All right. So then we can also look at, of course, D4, and we can say, okay, is this guy going to be abelian? Well, then we start going through and we say, okay, red and then blue versus blue and then red, and already we're not in the same place, right? Red, blue, blue, red. So this guy is not abelian. And I'll leave it to you to kind of walk through this and make a decision on whether or not it is abelian. All right. So this is just trying to explain how we can go through a Cayley diagram and determine whether or not a group is abelian. Right. So structurally, these don't look very different. All that's really changing is the way in which the arrows are interacting with one another. So not only is there a need to see a certain kind of structure, but there's a need to see a certain kind of pattern. Right. What you can see is I have two outward going, and then they go out again. All right, so over here, I have two outward going, but it doesn't go out in the appropriate direction from here, right? This guy goes here, so he needs to go out. So there's a need for kind of, let's say, parallelism, right? What I can see is parallel, 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 parallel. Now, by parallel, I mean, let's say, same, basically, they're not going to intersect, but also they're going in the same direction, all right? So we have a need for this kind of parallelism in order for this to work out for us. All right. Now, abelian groups are pretty easy to spot if you look at their multiplication tables, because this property here means I need symmetry across this main diagonal. So let's think about it like this. If you just made a grilled cheese sandwich, I don't know, growing up for me, you always cut it diagonal in this way. I'm not sure why. I think it's because it's easier to dip into tomato soup, apparently. But the idea is, if you cut it in this way, then they should be mirror images of one another. So when I'm looking at a multiplication table, I can draw this diagonal line, and I can ask myself, if I fold along this line, does everything match up? And in this situation, it does for every single element, so it is abelian. All right. So what we have is abelian has this very nice symmetry because of the symmetry of this operation. All right. So what do we have so far? We've had cyclic groups, which are very simple. They're basically the integers modulo n. We have abelian groups, which are let's say groups in which the order that we do things don't matter. So we're talking about addition of real numbers, addition of integers, addition of matrices, multiplication of real numbers. But then things that fail to be abelian would be things like matrix multiplication. All right? And so the next thing is something called a dihedral group. All right? So cyclic groups describe 2D objects that have rotational symmetry. Dihedral groups describe 2D objects that can be rotated and flipped. Okay? So we not only have this rotational aspect to it, we have this flipping aspect to it as well. Now, one of the things that you should immediately have come to your mind are what are called the regular polygons. So what do I mean by regular polygons? Equilateral triangles, squares, regular pentagons, meaning that the angle at each corner is exactly the same, and so on. So the regular n-gons are things where all of the interior angles are the same and all the side lengths are the same. And we represent the dihedral group, or the regular n-gon, as d sub n. Now, c sub n lives inside of d sub n. Why? Because you can rotate all of these objects, so there you go. You have part of c sub n, which is just that rotation. However, the fact that I can flip it introduces another set of actions, right? So if there's n actions here, then what happens is, so you can think c sub n has a rotational direction like a clock. Or let's say clock is this way. All right, and then when I flip it, right, so when I basically turn it upside down, if I'm rotating this way, when I flip it upside down, I start rotating this way. But in the language of groups, that different direction of rotation introduces a brand new set of actions. So if this guy has n actions, then flipping makes each of these n actions now be brand new. All right? So basically what this means is I have n rotations and n reflections. So we can decompose our dihedral group into the rotations, which is just the orbit of R, and then all of the reflections, which is doing what? Take each element and flip it. So take this guy and flip it. take r and flip it, take r squared and flip it, and so on. So we have this new group that has, of course, this one orbit here and then a bunch of little pieces over here. So D3, which was, of course, the equilateral triangle we've already seen. D4, which was the symmetries of the square, which you drew last semester, we've also seen. All right, so we have these very expected looks, right? There's kind of circles, an inner circle and an outer circle, and then you draw all the spokes in your wheel, right? So it's kind of like this rim has 3 spokes, this rim has 4. Now, something you don't need to worry about as much is what's called the infinite dihedral group, which you've also seen. And what you should kind of see here is this is somehow one circle, and this is another circle, right? This circle goes one way, this circle goes the other. So if you imagine them being of infinite length, then somehow they're allowed to be kind of side by side in this way because this guy wraps around at infinity, but it's somehow smaller. And this guy wraps around at infinity, but is also somehow bigger. So this is your D infinity, which of course would be very difficult to draw. All right. So now, if S and T are 2 reflections of an n-gon, so what do I mean? So what I mean by 2 reflections is I've chosen 2 reflections over here. All right. So then the idea is we need some kind of notion of adjacent axes of symmetry. All right, meaning that their axes are incident at pi over n radians. So what does that really mean? This means that somehow they line up so that if I do these reflections, it'll coincide with some of the original rotations. All right. And that's exactly what we're saying. So if they kind of coincide in that way, then performing 2 reflections ends up being equivalent to just a single rotation by a particular angle. And that angle corresponds to how they kind of line up. All right. So to see an explicit example, let's think about doing a rotation and then a flip, and then just a single flip. Now, what we had said a long time back was actually that D sub n can be generated by the rotations and the flips, where we think of there is this cycle of just the entire rotations, flips reverse themselves, and then a rotation, flip, rotation is the same as a flip. All right. So these 3 things can actually generate the entire group by being the only pieces of information you use and use them over and over and over again. So from this it follows that if we perform rotation and then a flip, we get rotation, flip, flip, which because of associativity is rotation, flip, squared. But what do we have? Flip squared is E, and R against E is R. So this, of course, was once again a rotation. So what this means is any D sub n can be generated by 2 objects. Pick a random set of flips that have this particular kind of property. Then the idea is performing them twice sends us back to E, and then performing them over and over again in this order generates the entire group. All right. So basically the idea is all the rotations are things of this form, and all the reflections are just these guys performed over and over and over again. Now, I'm obviously not going to be asking you to do something this abstract. This is just kind of filling in the gaps in terms of those of you who are more interested in knowing what are really the manifestations of these objects. Now, in the more explicit and concrete setting, what we're really talking about here are the regular n-gons, equilateral triangles, squares, pentagons, and so on, or any group whose Cayley diagram can be drawn as a regular n-gon. All right, so it doesn't have to just be the shape. It's also any group, no matter how abstract it is. When you draw its Cayley diagram, if you can draw it as a regular n-gon, then it is in fact a dihedral group. All right. So, and then basically, let's say there's a lot of details here, but I could ask you, what would the Cayley diagram for a general dihedral group look like? Right. So remember, this is just what we said. General dihedral groups can be done in terms of just 2 reflections. So I'm saying, okay, we have our 2 reflections that generate the sets of rotations and the sets of reflections. So what would it look like? Well, one thing to note that you may not necessarily know is that once n is bigger than 3, meaning what? Once it's not a triangle, then it's not a billion, because rotations followed by flips or flips followed by rotations are not the same thing. However, one can prove this is the following thing. We have the following identity. All right, where n is the number of elements, then the idea is moving r over, you have to replace it with basically the 1 with an n minus 1. So there's a very much nice pattern here, but it's not quite a billion. All right, and you might say, well, what is this for? Well, basically what you have to think of is if I do one rotation and then a flip, to make it equivalent to a flip and then a rotation, I have to basically go all the way around my object. And so this corresponds to the amount of space that's left to go all the way around the object. I've already went one, so now I need to go in more in order to make this reversal equivalent. All right. So, and the idea is looking at Cayley graphs of D sub 3 should make this pretty obvious, right? We had some Cayley diagrams, so you can convince yourself of this fact, right? So what do we have? Well, in n being 4, this would mean that RF is equal to FR cubed. All right. So if we do RF, this is equivalent to doing FRRR cubed. So we can see already that there's a very natural thing, and it's because I have to traverse around the entire outer ring in order to make this work. The reason it works in this nice situation is because of the smallness of the actual ring. All right. So, it's not a billion, but this still holds. We still have to traverse around. Now, what do cycle graphs of dihedral groups look like? Well, I like to think, I always call this kind of like an engagement ring, or I guess just any ring. I think the engagement's the one that has the diamond. Yeah. So the idea is this is simply a ring. So the idea is the dihedral group consists of an orbit, which is just a copy of the cyclic group, which forms the kind of band down here at the bottom. Then, after that, each of the flips are only orbits of size 2. So this is one of the flip orbits, 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 and so on and so forth. So the cyclic group, the dihedral groups actually have very nice cyclic diagrams. All right. And it's actually the case that down here, there may be suborbits as well, right? So I see the orbit of R, but there's also inside of it the orbit of R squared, right? So somehow I can't distinguish between them because they live in the same space, but what I have are two distinct orbits living here. All right, so that's important to know. Now, multiplications of tables of dihedral groups actually don't look quite as simple as you hope they would. Basically, when we're looking at this pattern here, it's somewhat difficult to deduce what kind of pattern may or may not be present. But basically what happens is I can decompose it into the following. Here I have the non-flipping objects, and then down here I have another non-flipping object. Right? These are all these kinds of rotations. And then up here I have flips, and then up here I have flips. So if I really think about generalizing this, I have kind of non-flips, flips, flips, and non-flips. All right. Now, if you shrink this down and call this kind of, let's say, one action, let's call it E, let's call this F, let's call this F, and let's call this E, then what this actually looks like is when you shrink these down, this is exactly equivalent to the Cayley diagram for your swapping a penny and nickel, right? There was the swap and the no swap, and there was just four distinct, or let's say the Cayley diagram had 4 spots for the 2 distinct outcomes. So this giant thing, in some sense, looks equivalent to this much smaller thing. And this shrinking that I'm referring to is something that we will talk about later, and it's called taking the quotient of a group. All right, so you don't have to worry about that now. This is just to allude to something that we will be discussing later. All right, so we have cyclic groups, which are basically the integers modulo n. We have abelian groups, which are very nice groups in terms of having commutativity of their operations. Then we have dihedral groups, which are basically your regular polygons. And then now we're going to talk about symmetric groups. So, symmetric groups are basically groups that can be seen as being collections of ways of rearranging things. All right? So, we need to formalize this in some way, and we do this by introducing the notion of a permutation. So, a permutation is an action that rearranges a collection of things. So if you have a, let's say a set of numbers, 1, 2, 3, then a permutation is any rearrangement of the numbers 1, 2, 3. Or another way of putting it is a permutation is a bijection from one set into another. Now, typically what we do is we denote the permutations by labeling everything with positive integers. So if you have a bunch of toys, you label them toy 1, toy 2, toy 3, and so on. And then permutations are simply rearrangements. So the idea is I can rearrange 1, 2, 3, 4 by sending 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So the idea is the set 1, 2, 3, 4 gets permuted to the set 4, 1, 2, 3. I can send the set 1, 2, 3, 4 to the set 1, 3, 2, 4, or I can send the set 1, 2, 3, 4 to the set 4, 3, 2, 1. All right? So now there's all kinds of permutations, right? These are not the only permutations of the numbers 1, 2, 3, and 4. These are just examples. All right? So permutations are rearrangements. And a rearrangement is simply anything that if I start with the numbers 1, 2, and 3, 4, I end up with exactly the numbers 1, 2, 3, and 4, but in a different order. All right, so these are permutations, and symmetric groups can be thought of as just being equivalent to the set of all permutations on a given set of numbers. All right, so permutations are just rearrangements of these integers. So what I'm going to do before introducing the notion of the permutation group, I'm going to add to what we had in the notes by actually giving you some more background on permutations. So I didn't put this in the notes because, for one, it's not necessarily important because I'm not asking you to do lots of, let's say, computations and algebra with them. But it is possibly helpful to understand what these things are on a deeper level to help you understand what's going on. So in order for the set of permutations on n objects to form a group, which is where we're trying to go, right? So the idea is if you fix the number of integers you have, you want to look at all the permutations or all the bijections. And what I want that to be is a group. So then what I need to do is understand how to perform a binary operation, which means I need to understand how to combine permutations. So as an example, what should this permutation followed by this permutation be equal to? Now, here's how you should be thinking of this. When you're defining operations or permutations, the idea is what? I start with the numbers 1, 2, 3, 4. A permutation maps 1, 2, 3, 4 to a certain arrangement. So what I'm trying to say is let's call this permutation F and let's call this permutation G. I'm asking what does F times G give me? All right? Well, here's what you should really think about. I'm going to do the following. I'm going to take the number 1, and this is going to send 1 to 2. So now I want to know what this guy's going to do to 2. This guy's going to send 2 to 4. So the entire outcome should be that 1 goes to 4. Similarly, 2 goes to 3. And then if I apply this permutation, 3 goes to 1. So the outcome is that 2 goes to 1. So what I'm trying to say is when we combine permutations, there's this kind of chaining or composition feature that is the outcome. All right? And so the idea is this permutation, right? This was the permutation here, combined with this permutation, where I'm just using the general star to be this combination, is the following outcome. Remember, I said that 1 got sent to 4, 2 got sent to 1, and then you could similarly figure out that 3 goes to 2 and 4 goes to 3. And so this breakdown is exactly what I just tried to describe. We're going to send 1 to 2. This is going to send 2 to 4. So the outcome is that 1 goes to 4. It's the net outcome. All right. Now there's an order of operations here. Right. These are not necessarily commutative. So the idea is you do the left first and then the right second. Okay. So there's a very clear order of operations. All right. Now, to let you know, and you should probably know this from your basic intro to stats class that you took probably back in like your freshman year of high school, there are n factorial possible permutations of n items. So there's n factorial. Remember, what does n factorial mean? It's probably easiest to define it through an example. 5 factorial is 5 times 4 times 3 times 2 times 1. So the factorial is somehow this kind of, let's say, iterative multiplication. All right. Now, so on n objects, there are n factorial possible permutations, and the collection of these n factorial permutations forms a group. All right. So to verify this, we need to check that the appropriate rules of one of our definitions of a group holds. Okay. So which one should we probably go with? Well, it seems easier to, I mean, it doesn't really matter which one you want to go with. But basically, we need to have some notion of an inverse at the very beginning, right? We need to either reverse the action or have the inverse with respect to the binary operation. So how do you invert a permutation? Well, you simply reverse the direction of the arrows, right? So if this guy sends 4 to 1, its inverse sends 1 to 4. If this guy sends 1 to 2, its inverse sends 2 to 1. Clearly, this is still a permutation, so I have a permutation and its inverse permutation. All right? So then you might ask yourself, is there an identity permutation? Yes, it's the permutation that does nothing. All right? Is our operation associative? The answer is yes, it's associative. This would take some time to prove in rigor, but I think just from our previous example, it should be pretty clear that we would have associativity because we just kind of chain along left to right. It doesn't really matter kind of what you do first as long as you're moving left to right throughout all these operations. All right. And is it closed? Well, yes, as long as I have these permutations, I don't necessarily somehow magically introduce the number 5, so I will have a notion of closure as well. So we have closure, associativity, we have identities, we have inverses, so this is in fact a group. So the group of all permutations of n objects is called the symmetric group on n objects, and is denoted S sub n because of the word symmetric. All right. Now we've already seen the symmetric group S3, which just so happens to be the dihedral group D3, but this is the only time in which these two coincide. All right. Just is pure coincidence almost that the equilateral triangle exactly represents all the possible ways you can permute the numbers 1, 2, and 3. All right. Now, another thing to note is even though the set of all permutations forms a group, it's not the case that a group of it's the case that there are groups of permutations that do not require all permutations. So let me be very clear here. The idea is the set of all permutations on n objects is a group. However, you can take a subset of all permutations on n objects and can also have a group as long as you choose that subset very carefully. So I'm not saying any subset, I am saying that there are other subsets, okay? So I'm not asking you to know how to form all these, I'm just simply letting you know that there could be others, all right? So, for instance, the cyclic group and the dihedral group can both be thought of as certain sets of permutations. So the idea is that we can realize both of these guys as permutations. Right, and the cyclic group should be pretty easy. So what I mean is they're just the rotations, right? Send everybody to its neighbor. Right, the dihedral group can be thought of as sending everybody to his neighbor, but also flip-flopping some guys as well. So we not only have kind of these unidirectional arrows, right? We also have the ability to flip-flop two objects, all right? So these, of course, can be thought of as permutations, and we already know they're groups. So if we can relate them to permutations, they're not the entire symmetric group, which is what I'm saying up here. So these are somehow permutation type groups, even though they're not symmetric groups. So now this observation is not something I expect you to prove, but it is an observation that I want you to understand because it comes in handy later. All right? So now, we can also provide what's called a cycle notation for permutations. So the idea is as follows. I can represent this thing, which sends 1 to 2, 2 to 3, 3 to 4, and 4 to 1 as 1, 2, 3, 4. And the reason that I understand it this way is because it sends 1 to 2, 2 to 3, 3 to 4, and then 4 goes off the side to 1. All right? Now, as another example, let's say, skipping this observation for a minute, if I'm looking at the cycle, or let's say the permutation that sends, follow the blue arrows, sends 1 to 4, 4 to 6, 6 to 5, and 5 back to 1, then I'll write it as 1, 4, 5, 6 because of the order in which it moves. Or sorry, 1, 4, 6, 5, right? Because it sends 1 to 4, 4 to 6, 6 to 5, 5 back to 1. All right? Now, an observation is that every permutation can be decomposed into a product of disjoint cycles. So what do I mean? So let's consider the following permutation. So here is a permutation on 10 objects. So I have that 1 goes to 4, 4 goes to 6, 6 goes to 5, 5 goes to 1. I have 2 and 3 flip-flop, and I have that 8 goes to 10, 10 goes to 9, and 9 goes to 8. I can represent these as disjoint cycles, as these three things. And you might think, what does disjoint mean? It means that there are no numbers in common, right? There's no 2 in either of these other objects other than the red one. Now, I'm not asking you to be able to decompose them this way. I'm just simply telling you that you can decompose them into this way, all right? And another thing to note is since they're disjoint, since they have nothing in common, the order in which I perform them does not matter, right? So the idea is since they're not interacting in any way, then clearly I can do them in any order. Right? So this is kind of like going back to the clothes analogy. Since putting on your socks has nothing to do with putting on your shirt, unless you're putting on your shirt in a very strange way, the order in which you do them will not matter. So we can decompose, let's say, putting on our clothes into a set of disjoint cycles. Right? And so the socks and shoes are not disjoint, so they're stuck in the same cycle. Similarly, let's say underwear and pants are not disjoint unless you're Superman. Or not Superman, right? Superman just does them in the opposite order. But the idea is if you want to wear underwear, you have to put them on before your pants, right? Of course, if you're wearing something like a dress or a skirt, that is not pants. I'm meaning something that has closed legs that prevent the ability to put a pair of underwear on. So anyways, I'm getting kind of a field from the point. The point is that we can decompose these permutations into these kinds of cycles. All right. So, and so then the idea is, what if we want to actually compose things in cycle notation? Well, first, we should note that these two things are equivalent. So what I can do is I can say, all right, sends 1 to 2, 2 to 3, 3 to 4, 4 to 1. So here is its cycle notation. This sends 1 to 3 and 3 back to 1. So I have a 1, 3. 2 to 4 and 4 to 2. So I have a 2, 4. All right. So how do we actually perform this product? Well, we read left to right. So this sends 1 to 2. 2 skips over this guy, and 2 goes to 4. So I have 1 to 4. All right. This sends 2 to 3. This sends 3 to 1. So I have, this sends 2 to 3. And, where am I going? This guy sends 2 to 3. This guy sends 3 to 1. So we have what? That, wait, I am reading this backwards. Right, so this sends 1 to 2, this sends 2 to 4, this sends 2 to 3, this sends 3 to 1. And so the outcome of this is that 1 to 2, I'm sorry guys, I may have made a typo on this slide. So this sends 1 to 2, this sends 2 to 4, so 1 goes to 4. 2 goes to 3, 3 goes to 1, so this has 2 going to 1. There we go. This sends 3 to 4, and this sends 4 to 2. So this has 3 going to 2. There we go, right? So what do we have here, right? The idea is, so once again, we have 1 going to 2, and then 2 going to 4. So I have 1 going to 4, all right? Then I have what? 2 going to 3, and 3 going to 1, so I have the 2 wrapping around a 1. This sends, let's see, 3 to 4, this sends 4 to 2, so I have, this sends 3 to 4, this sends 4 to 2, so I have 3 going to 2. This sends 4 to 1, this has 1 going to 3, and this has 1 going to, 1 going to 4. Wait, 1 to 2, yeah. I think I've repeated myself, and I'm sorry. I've obviously rambled on this slide. What I'm trying to say is we read left to right. So once again, 2 goes to 3, 3 goes to 1. So in total, 2 goes to 1. So 2 wraps around the back to 1. 3 goes to 4, 4 goes to 2, so we have 3 going to 2. All right, 4 goes to 1, 1 goes to 3, so I have 4 going to 3. All right, so once again, I'm not really asking you guys to decompose these things. This is just to let you know that we can define products and decompose them in this way. And this will be important for something I want to discuss in a minute. So, a transposition is a permutation that only swaps 2 objects. All right, so for instance, just something that leaves everything unchanged, but it just swaps 2 numbers. So going all the way back, this is a transposition. It leaves 1 and 4 unchanged, but it swaps 2 and 3. All right, so in cycle notation, a transposition is just a 2 cycle, and the entire group of permutations on n objects can be generated by transpositions. All right. So intuitively, this means that all permutations are just successively exchanging pairs. So for any of you guys who maybe have taken a computer science course and you've written a sort algorithm, then this is exactly true, because you know that every unsorted list can be sorted by performing simple swaps. All right. So in fact, we only need the adjacent swaps to actually generate the entire group. So the idea is if we want to generate the symmetric group on n objects, we can simply consider all the pairwise, meaning neighboring swaps, and if we do all of those in appropriate orders, we will get the entire group. Once again, I know that maybe I'm going into too many details here, but I think some of you guys have been struggling with symmetric groups, so I want to give you guys some more notes in these slides to go back and reference. All right. So, and even though we can do this, there could be lots of ways of doing it. So what do I mean? This can be written as this, can be written as this, can be written as this. All right. Now, even though there's a ton of ways of doing it, the parity of the number of transpositions for a permutation is fixed. All right, so what do I mean? If I have one representation that has an even number, all of my representations will have even numbers. If I have a representation with odd numbers, then all of my other representations have odd numbers. So we can basically group permutations into two distinct sets. Those that have an even number of transpositions when we represent them, and those that have an odd number. And we call transpositions that are composed of an even number as even permutations, and the ones that have an odd number as odd permutations. And here's what you should kind of see. Since there's an odd number of elements, we get an even number of transpositions. Okay. Now, at this point, I've put a practice slide here where, of course, you can question me about it later. I'm not going to go through and describe it because that would not be terribly helpful for me to put words into thin air. But basically, I want you to try and get a better understanding for the symmetric group S3. All right? And to do this, basically, I want you to think of the following. I want you to draw its permutation picture. All right? So what do I mean by that? Well, draw its Cayley diagram. I want you to write out every single permutation through disjoint transpositions. So 1, 2, 2, 3, and 1, 3. So decompose all of them. I want you to write it as the product of disjoint adjacent transpositions. So decompose all of them into just 1, 2, and 2, 3, and determine whether each of these is even or odd. All right, so obviously I'm not taking this up. This is to help you understand permutation groups better. All right, now, and move into the next slide, I give you another practice problem, which is write down the alternating group A3, which I just tell you is the group consisting of only the even permutations. So basically you have 6 objects in S3. 3 factorial is 6. 3 of them will be even, 3 of them will be odd. The 3 even ones correspond to A3. All right? And so I haven't told you what an alternating group is yet, but I'm telling you that the even ones form this thing. And what I'm asking you to do is now draw its picture and tell me what group this is isomorphic to. All right? So, of course, at this point you can pause the video and try and do the practice, but this practice is simply here because I think it would help you get a deeper understanding of all the stuff that I've just described previously. All right, so now that we have symmetric groups, we're obviously from the previous problem going to introduce alternating groups. And now I can give you a better definition of the alternating groups than I did in the notes. So exactly half of the permutations in Sn are even, and they form a group called the alternating group. All right. So how do we verify? So first of all, the definition of the alternating group is the set of even permutations on n objects. All right. So rather than the squareable ones that we had for the very small symmetric groups, this is the exact way in which you can visualize it as the even permutations. All right. So how can we verify that this is a group? Well, of course, we need to make sure that we have a binary operation. And here's the kind of thing. A sub n is a subset of S sub n, which means that it already has a binary operation, and that binary operation is associative. We already have inverses, and since inverses are just reversing arrows, the inverses will also be even. We have identities, so of course the question is, what is the order of the identity? Well, you can convince yourself that the identity, which is the do-nothing action, consists of 0 transpositions. Hence, 0 is even, so it is inside of A sub n. So the only other thing that's of concern is the closure. Can I combine even permutations and end up with an odd permutation? So that's the question that we're asking here, right? So I'm claiming it's a group. I'm telling you that all the other properties of groups are kind of given except for closure. All right? Now, so what you should be thinking here, this is kind of like way back in chapter 1 last semester when we showed that the integers with addition had all these nice properties of a group. But then when we looked at the even integers, it also had this nice property, but we had to convince ourselves of this fact. Also, for one of your homework problems, it may be worth noting, since A sub n is the even and exactly half are even, the order of A sub n is n factorial divided by 2. So, now, let's say the closure part is something that we can convince ourselves of, but it's not something I'm going to bore you with. And you can do a few practice problems to see that it is in fact still true, but here's what you should kind of think of. If you have two even permutations, then you can decompose them into an even number of transpositions. So the product of these two would have the product of two even numbers, which is once again even. So this is why we have closure. Now, the interesting fact that I gave you in the notes was that as long as n is less than or equal to 5, then the alternating group is just the set of squares in the symmetric group. So what I mean is, if I take the original element and I square it, right? So this is the identity. I did nothing. So the identity squared is nothing. If I take this guy, which is flip 1 and 2, if I flip 1 and 2 again, they go back to their original space. This guy is flipping 2 and 3, and if I flip again, I get 2 and 3. Once again, flipping 1 and 3, flipping it back. This does 1 to 2, 2 to 3, 3 to 1. And if I perform that again, right, so what do I mean? It would send 1 to 2, and then that sends 2 to 3, which the ultimate outcome is that 1 ended up at 3. And similarly, so this is our new permutation, and this is our other. So what I have, the squared elements, I got 4 of the same, and then 2 distinct ones. So I had originally 6 elements, and now I have 3 distinct elements. So for S sub 3, A sub 3 just consists of these 3 elements. And you can convince yourself once again that these come from an even number of transpositions. All right. Now the alternating groups are kind of important because basically they describe the symmetries of the 5 Platonic solids. All right. The symmetric groups and the alternating groups. So what do I mean? So there's only 5 three-dimensional shapes of which all the faces are regular polygons and meet at equal angles. All right, so what do I mean? So a tetrahedron are triangles that are glued together, that all the triangles are the same, and it's exactly equivalent. A cube is 6 squares glued together. An octahedron is 8 triangles glued together in such a way that they all have equal angles at every single point. Right? A dodecahedron is a pentagon with 10 pentagons, and then similarly here we have 12. And then icosahedron is a bunch of triangles, right? I'm tripping over my words here a little bit. The actual idea, though, is you have seen these shapes before. I imagine many of you guys have taught geometry at the middle school or high school level, wherever it's taught now. But the idea is these are the only ones in 3 dimensions where you can do this. In higher dimensions, you can do it more. But the symmetric groups and alternating groups can be represented with Cayley diagrams that coincide with these objects. So they kind of have a certain number or a certain importance with these geometric objects. So the groups of symmetries of the Platonic solids are, so what do I mean? All the different ways that I can rotate this object, flip this object, and it still occupy the same 3-dimensional space. Well, the tetrahedron has the alternating group of size 4. The cube has the symmetric group of size 4. The octahedron has the symmetric group of size 4. And the last two have the alternating group of size 5. So even though these objects are different in terms of their overall shape, they actually have the same number of symmetries or some certain symmetries in common, right? These two and these two actually have the same kinds of symmetries, all right? Now, the Cayley diagrams for these 3 groups can actually be arranged in some very interesting ways. And let's say this is more of an interesting fact rather than, let's say for our class, something that will just be fundamentally important, but it helps us understand more about these groups. So the Cayley diagram for a particular Platonic solid X can be arranged on a truncated X, where truncated refers to cutting off some corners. So what do I mean? The Cayley diagram for the cube can be thought of as taking the cube, and then at every corner we're going to make a slice. And that's going to represent some kind of object of that slice that we make. So the cube's going to have all these slices at each of its 8 corners. All right. The octahedron's going to have some slices at each of its corners. The tetrahedron will have slices at its corners, and so on. So what do I mean by these Cayley diagrams? Once again, I'm saying, okay, here is a configuration of the tetrahedron, and I'm going to basically perform a rotation that is counterclockwise where it preserves this kind of orientation. And now I have a new configuration of the tetrahedron, and so I can draw the Cayley diagrams of all these actions. So For instance, for A5, so this is the alternating group on 5 elements. So first of all, let's ask ourselves, what is the order of A5? Well, A5, or let's say S5, has order 5 factorial, which is 5 times 4 times 3 times 2 times 1, which is 120. All right. So now that we have 120 elements in S5, A5 has 120 divided by 2, which is 60 elements. All right. And if you want, you can try and take the time to convince yourself and try and count all these nodes and see if there are 60 of them. So what do we have? Well, looking at this icosahedron, think about slicing all the corners. All right. So if we think about slicing all the corners, the reds are all the slices, right? The icosahedron, if we think about kind of making a slice of these reds, then we end up with some red, these kind of red loops in here, and then we have these red and blue interlacing loops of the original spaces, all right, from the slice, right? And so what we can see is these slices, they change the actual shape face, right? These were triangles, and now when I make slices, a slice, a slice, a slice of a triangle adds 3 more sides to give me this hexagon. I have this interesting kind of soccer ball shape. The icosahedron can also be done the same way. Or sorry, the dodecahedron, I mean. So what I mean is at each corner we're going to make slices, which of course are going to change the objects once again, and we have that these are another way of configuring this. Now the real interesting part of this is the following. These are exactly the same algebraic objects. These are both A5's Cayley diagrams. They just look slightly different. So I in the notes have described more about how this works, and of course I'm not asking you to draw these objects. This is just to simply let you know that these are 2 different representations for very complicated Cayley diagrams. All right. Now, the last thing is Cayley's theorem, which is very important, but something that can seem complicated and that I've written a proof for in the notes. So you can look at the proof in the notes to get a lot more of the details, but I want to provide some general ideas about Cayley's theorem. All right. So, a set of permutations that forms a group is a permutation group, and we've defined that, and it's called S sub n. Cayley's theorem says that permutations can be used to construct any finite group. So, in other words, every group has the same structure or Cayley diagram as some permutation group. All right. Now, the thing here is the set of all permutations is S sub n, but remember we said that there could be permutation groups that don't require all of these permutations. So Cayley's theorem could be considering these as well. All right. So we're not saying that every group is isomorphic to some S sub n, right? For instance, we know that there are lots of groups with particular orders, for instance, order 5, which I can't construct from something like n factorial or n factorial divided by 2. So they're not just symmetric to permutation groups, but groups of permutations. All right. So then, of course, the question is, given a group, how do we relate it back to permutations? Now, before we move on, let's say you might think, why would I care about this? Permutations, after you begin to understand them, are fundamentally very simple objects. They're things that have existed for a long time and things that we understand very well. So, if I can relate all algebraic objects to permutations, then that means I have a common ground with which I can do lots of interesting and simple things. So before the existence of software and computers, people knew how to work with permutations, but they didn't know how to work with these other more complicated groups. So knowing that I could always map them back to permutations was a very exciting and important thing because it allowed me to perform computations and arithmetic. All right. But for us, let's say in the modern age of software, this is really more of a interesting novelty. All right. So how do we construct let's say, from a Cayley diagram, how do we associate all of its permutations? All right. So the idea is as follows. If we have n nodes, we're going to give them numbers 1 through n. So here we're going to do 1, 2, 3, 4, 5, 6. Interpret each arrow in the Cayley diagram as a permutation. All right. So how do I go about that? Well, with D3, I know there's only rotations and flips. And so what I'm going to do is try and see that what these things do. Okay, well, the red arrows as permutations send 1 to 2, 2 to 3, and 3 to 1 over and over and over again. So I have the permutation 1, 2, 3, and they send 4 to 6, 6 to 5, 5 to 4. So I have this permutation. Now, the blue arrows simply flip-flop things. 1 and 4, so 1 to 4, 4 to 1. 5 and 2, 6 and 3. All right? So D3 is isomorphic to the subgroup. Once again, I haven't defined this, but the idea is it's the group of permutations that's generated by this permutation, and this permutation. All right? And the idea is all of these live inside of S6. So it's not all of S6, but it lives inside of it. And so you, of course, would have a very hard time writing down all the elements, but you could tell me in your own words that this thing is equivalent to the, let's say, group that lives inside of S6 whose generators are these guys and these guys. All right, so we have a very nice construction of this group, and the idea is what we see is the red corresponds to the rotations, the blue corresponds to the flips, so we have very clear single objects that correspond to the single generators. What you can think to yourself is, if I had more than 2 generators, that would be very odd because I'm somehow saying that they're equivalent, but one group has 2 generators and the other one has not 2. So the preservation of structure includes the preservation of the number of generators. All right. If we have a multiplication table, it's pretty much the same process. Replace the headings with 1 through n, and then inside of the table, whatever you called 1 on the headings, you need to go through and find it in the table and recall it 1. And then take each column and interpret it as a permutation. And once again, this would be a bijection between the original group and the generators of the permutations. So what do I mean? So this is V4. This is the thing about, let's say, kind of manipulating squares, right? So this is your Klein 4 group. And the idea is pretty simple. We want to think about relabeling everything, and so let's say you don't need to worry about what's happening here. I've relabeled my multiplication table, and I've went through and relabeled everywhere else. So my permutations tell me that it's going to send 1, 2, 3, 4 to 1, 2, 3, 4. So the first column is the identity. The second one tells me I'm going to send 1, 2, 3, 4. So I'll send 1 to 2, 2 to 1, 3 to 4, and 4 to 3. So I have these 2 swaps. This sends 1 to 3, 2 to 4, 3 to 1, and 4 to 2. And this sends 1 to 4, 2 to 3, 3 to 2, and 4 to 1. So we see that V4 is isomorphic to the subgroup of S4 generated by this permutation, 1, 2, 3, 4, and this permutation, 1, 3, 2, 4. All right? So, and the idea is, you might say, well, how did I get that? Well, this guy's decomposed, this guy's decomposed, right? So we have the 1, 2, and the 3, 4. This guy's decomposed. We have the 2, 3, and the 1, 4. This guy is also decomposed, right? So we have these nice kind of decompositions here, all right? And so we need to simply just convince ourselves that everything will work out, right? So the idea is, even though this is a different decomposition, it can be represented in terms of these 2 decompositions, all right? And let's say, once again, since I'm not going to be testing you on your ability to decompose these things, this is going to let you know that you can do it. All right, so once again, in these notes, I'm not trying to add complication. I was hoping that by adding details, it would provide some clarity. If we want some exercises with respect to the more detailed explanations, you can let me know and I can try and provide them. All right. So, intuitively, 2 groups are isomorphic if they have the same structure or same Cayley diagrams. Now, I haven't defined isomorphic yet, so I'm just giving you a notion of it for now. So Cayley's theorem says that every finite group is isomorphic to a collection of permutations. All right. Now, the isomorphism is really something as follows. An isomorphism, what we'll learn later, is a bijection, which, of course, mathematically just means relabeling, and it preserves the algebraic structure, which means it has the same Cayley diagram. So basically, we need to find an explicit way of relabeling, which is exactly what we've just done, right? I've provided 2 explicit algorithms that allow me to relabel and get new objects, right? Or new permutations. So we haven't shown that this is a group by any means, but I, of course, proved this in the notes, at least very loosely, so I can refer you to that, all right? So Obviously, if you find typos in this, let me know, or if you find typos in the notes, let me know. I've already had one email, I think, regarding one typo where I should have written inverse somewhere, so I'll update the notes. Once again, I'm sorry if I have added confusion with these notes. I know that there was a lot in this chapter. What I'll probably do is give you guys another week to work on these problems because of my delay. But what I'm wanting you to do is really just take the time to understand these groups. That's the whole purpose of this chapter, is to understand the groups. Not necessarily that you can do all the interesting math with them, but to understand fundamentally what these 5 groups are, and then perform the very simple manipulations that I'm asking you to perform. All right? So if you have questions about anything, of course, email me, and I will get back to you as soon as I can.